Hi, welcome to my talk on shear induced demixing in polymer blends. The main objectives of this talk are 1. To introduce a new framework for describing the flow of inhomogeneous polydisperse and bidisperse polymer blends, and 2. To explore, using that model, the physics of shear induced demixing in polymer blends with a shared monomer basis, for example, melts of polystyrene or melts of polyethylene. So, to begin with, I want to establish that flow-induced fractionation and flow-induced demixing are not purely academically interesting subjects. These have real industrial relevance as well. In particular, this phenomenon called die drool. So if you are extruding a polymer through a die, then what can happen is that you will get this buildup of polymer on the die face that's sort of leaking out of the extruder. And it's called die drool, and we don't know all the details of how and why this forms. We know that it's a problem. It will potentially mar the surface of your extrudate. It can char onto the surface of the die face. It can do all kinds of different problems. And one of the few things that we absolutely know about this consistently is that if you compare the molecular weight distribution of polymer within this die drool to the molecular weight distribution either of the virgin pellets, the extrudate core, the extrudate skin, you'll consistently find that it has a lower average molecular weight and a completely different molecular weight distribution as well. So it's a different collection of polymers that are sort of leaving the bulk melt in order to deposit themselves on the die face. Shear-induced demixing will happen even in something as simple as a simple shear flow, and it's been shown experimentally in systems of polyvinyl methyl ether mixed with polystyrene. They've seen this experimentally. But there's no reason that the same thing couldn't or shouldn't be happening in melts with just a single monomer basis, melts of polystyrene or polyethylene or something like that. But it's been less studied in that particular context, and so that's what we're going to explore in this talk. One of the principal challenges to modeling shear-induced demixing in a polydisperse melt is that it's even a challenge to build a constitutive model for the nonlinear rheology of polydisperse polymer blends. So that's the first thing we're going to talk about here. Because without establishing that, it's impossible to look at flow-induced demixing phenomena. So if you're looking at the linear rheology of a polydisperse polymer melt, there are some really well-established tools that you can rely on. In particular, the double reptation approximation is remarkably effective. And so what the double reptation approximation does is it says, okay, you've got this really complex topological environment with all of these different kinds of interactions between all of these different kinds of chains, but to get a good guess for the linear rheology, you can coarse grain all the topological complexity down into just binary pairs of entanglements. Chain A with chain B with chain C, and so on. If you catalog all the different pairwise entanglement possibilities, then you can describe stress relaxation at each of those entanglement pairs by simply an additive process. Right? That the relaxation rate for an entanglement is just the rate of relaxation when one of those chains reptates out of the entanglement or the other one reptates out. Now typically the double reptation mixing rule is represented as an integral constitutive mixing rule, but it can be equivalently represented in a differential constitutive form wherein the reptation rates just strictly appear as additive rates of relaxation. So what we do for a nonlinear constitutive model, and this work was done in conjunction with Daniel Reed and Victor Verdara over at the University of Leeds, is we simply generalize the microscopic picture of double reptation, namely these pairwise binary entanglements, to these nonlinear stress relaxation mechanisms of the roly-poly model. The convective constraint release picture is predictable. Its stress relaxation happens when either one or the other of the entangled chains moves past by chain retraction. The stress relaxation one is a little bit more interesting, and to our knowledge, this is kind of a novel picture of stretch relaxation in polydispersed polymer materials. The idea is that if you have stretch relaxing in one chain or the other, some of that slack that's introduced into the previously taut chain is going to be transferred over to the co-entangled polymer species. So the important question is, though, does this depiction of nonlinear rheology in polymer blends, does it actually work? And we've done some comparisons to the rheology of bimodal blends in steady extensional flows, or in transient extensional flows and transient shear flows over a wide range of flow conditions, and it does, in fact, seem to work. So now that we have a constitutive model with which we are satisfied, we can proceed to start building a two-fluid model. And in a two-fluid model, what we do is we once again remove all of the topological complexity of these fluids and put all of that complexity into this continuum depiction where each fraction of the molecular weight distribution is assigned an independent continuum fluid. And then all of these continuum fluids end up being coupled together by their relative motions being restricted by friction, and their collective motions are restricted by an overall incompressibility constraint. Okay, so before we proceed to the calculations and results from this two-fluid modeling framework, I want to begin with some back-of-the-envelope calculations. Sorry about this. Okay, back-of-the-envelope calculations. So the question is, how much contrast is needed before shear-induced demixing is a reasonable expectation? Assuming that something like shear-induced demixing arises as a prediction of the model, under what conditions might we expect it to happen? Okay, so the conditions where we would expect that to happen would be when the elastic forces, which are the only forces that can favor demixing, the entropic forces favor mixing, when the elastic forces are comparable in scale to the mixing forces within the system. Okay, but the elastic forces to drive migration, shear-induced migration or shear-induced demixing, must scale in some way with the chain contrast. If the chains are identical to one another, it's a monodisperse blend, then the concept of shear-induced demixing makes no sense at all. Right? So the elastic forces are going to go as kT per entanglement, ME is the entanglement weight, and they're going to be modulated by the excess polydispersity, so the polydispersity index -1. And then the osmotic forces are going to go as kT per chain, where MW here is the weight average molecular weight. So this is an average representation of the osmotic forces driving mixing, and this is a representation of the elastic forces that might favor segregation. If you simplify this down, what you get is that the excess polydispersity, so the polydispersity index -1, is approximately equal to 1 over the entanglement number. So when you have those two quantities comparable to one another, then you can expect that this may be a circumstance where it's viable to see some kind of shear-induced demixing effects. Okay, with that we'll proceed to some sample calculations. So these calculations here are for a steady, simple shear flow, so the geometry is drawn in the right here, where you have two infinitely parallel plates, and we're neglecting variation in the direction of flow and only looking at variation in the flow gradient direction. We apply a plane wave perturbation, and we see when does there exist a perturbation which could cause the system to go unstable. So that's the basic framework that we're starting from here. And in the figure on the left, we have the shear stresses scaled by the shear modulus relative to the Weissenberg number for the system, which is just a dimensionless shear rate. And superimposed on this rheological information, we have put information about the flow stability to shear-induced demixing. So regions in dashed red mark places that are unstable to shear-induced demixing. And we see there are two separate windows where the flow regime is unstable to shear-induced demixing. One at low shear rates, one at high shear rates, and then in between, the flow returns to be stable. So what's with these two separated regions? Well, the thing to remember is that shear-induced demixing, for flow-induced fractionation, let's start from flow-induced fractionation phenomena. All chains in the system want to get themselves from regions of high shear rate, they want to get themselves down to a region of low shear rate so they can be less stressed. Okay. But which chains can actually do it? all chains can't migrate in the same direction. Some have to migrate one way, and some have to migrate the other way in order to fill in the space left behind. So the direction of migration is determined by which of the species has the stronger driving force behind its migration. At low shear rates, one can imagine that the longer chains may have some appreciable alignment to them and some appreciable stress from that alignment, whereas the short chains will still be mostly isotropic due to the differences in their reptation times. Then you get up at higher shear rates and the long chains start to show shear thinning behavior, where changes in their shear rate have a marginal effect on changes in their configuration or their stress. And under those circumstances, the shorter chains, while they carry less stress, may have the larger driving force to move towards lower shear rates. Then by the time you get back up to high shear rates, the long chains start to actually stretch. You've exceeded the stretch relaxation time with the deformation rate. And so those long chains start to stretch, and then they once again have the stronger driving force to move towards lower shear rates, hence driving instability again. Okay, so with this established, let's look at the nonlinear dynamics of a shear-induced demixing instability that occurs within this low shear rate window here. Okay, so here we have, on the left, we're looking at a velocity profile relative to the gap position. So the flow geometry is tilted like this. And we see that over time it develops this banded velocity profile. A low shear rate where the long chain volume fraction is high, and a high shear rate where the long chain volume fraction is low. Remember, more long chains means a higher viscosity. Higher viscosity is going to mean lower shear rates. So that's roughly what we see consistently for shear-induced demixing in this low shear rate branch of the unstable flow region. Next, we're going to generalize these results to a polydisperse blend. So the previous results were for bidisperse blends, and one could naturally ask the question of, is this shear-induced demixing a peculiarity of a bidisperse blend, or are there some universal features that would translate to polydisperse blends? So to answer that question, we chopped up the molecular weight distribution of a polydisperse blend with a log normal molecular weight distribution. We've divided it into a set of fractions with equal overall volume fraction, and then each one of those is represented by the weight average molecular weight within that fraction, and we can build a multi-fluid model representation to describe flow-induced demixing phenomena. Once again, we'll superimpose information about flow stability to shear-induced demixing over the rheological information. This blend has a slightly higher polydispersity index than the one considered in the previous slide, and hence it has a wider region of instability at both low shear rates and up here at higher shear rates as well. And then the reasons for these separate windows are in fact the same as what we saw previously for the bidisperse blend. So going from bidisperse blends to polydisperse blends, it is more or less the same physics preserved and represented in each case for the linear instabilities. Moving to the nonlinear rheology, we do not yet have full nonlinear time-dependent calculations for shear-induced demixing in a truly polydisperse blend. But what we've done here for illustration purposes is we've taken the linear perturbation, this delta phi, that arises from the linear stability analysis, given it a small amplitude where it should be in its linear growth regime still, and added it on to the baseline molecular weight distribution to get a sense for how the molecular weight distribution is changing in the low shear rate and high shear rate regions of the flow. So in the high shear rate region of the flow, you still have what appears to be a more or less unimodal molecular weight distribution, just shifted to a slightly higher average. And in the low molecular weight region, you once again do have a lower peak, but it does seem to be developing this shoulder, which could potentially even turn into a bimodal distribution. So it would be really interesting to continue these investigations of this model and explore what might be happening in a truly polydisperse blend, the nonlinear dynamics of its shear-induced demixing instabilities. Okay, so just briefly to summarize, the most important result from this talk, if you remember nothing else, is this back of the envelope calculation, that when the polydispersity index -1 is comparable to 1 over the entanglement number, that's a circumstance where, depending on your shear rate, you may have shear-induced demixing in your systems. The next thing to remember would be that elastic effects in a system can favor either mixing or demixing. And in particular, favoring mixing, I've only seen that really a lot in bidisperse blends. I haven't seen predictions for that as much in polydisperse blends. In future work, there could be some really interesting stuff to do with boundary layers in model processing flows that may have direct application to flow-induced fractionation and things like di-Joule phenomena. And so with that, I'll close the talk, and I want to thank my advisors, my PhD advisors, under whom this work was originally done. So that's Gary Leal and Glenn Fredrickson, and their collaborators on developing the homogeneous flow constitutive model based on the double reptation model. So that's Daniel Reed and Victor Budara. So if there are any questions, please do not hesitate to contact me. I would love to engage more and discuss this work further with anyone who is interested. And with that, I'll thank you for coming and watching my talk, and I hope you enjoyed it. Thank you.